So over to Atulji.
Request all participants to please mute their microphones before Mr. Kulkarni starts. Request, please. Yes, please start, Dr. Kulkarni.
Good evening to all. It is nice to have a discussion on PVD, CVD technologies and their applications, because nowadays it is becoming very much popular in each and every field, right from say cutting tools to medical industry, industrial components or auto components, so on and so forth. So it is now becoming integral part of our day-to-day activities. One of the major application is a decorative also. So a lot of items what we brought in the house or those are the decorative, and those coatings are carried out through these PVD coatings only and technology. So now basically, as we know that today's industry is becoming modern with the help of artificial intellectual lean production, going from Euro 4 to Euro 6 means our Bharat 4 to Bharat 6, then various ERP systems that gives the attention to how we can able to become the cost effective. So if we see today we are looking for high volume production, where one of the major concern is a manufacturing cost as well as quality, keep the consistency right from one first product to the say 1 lakh of the product. So here normally what we look in day-to-day life is higher speed and feeds during the manufacturing, which supports to increase the productivity, then reduce tool inventory, there is a tool cost saving, then longer tool life, that is reduce the downtime, and improved part quality, that is a less scrap. So these are the nowadays vital and the most important task in the day-to-day manufacturing our activities. We keep on doing and concentrating on that one. So when we are using and doing all those things, a lot of adverse environment is there during the manufacturing. Like first one is abrasion. The lot of the wear we get due to the abrasion process or the abrasion condition. Another one is wear due to the thermal fatigue. Similarly, we can able to see that on the other side, wear is there, or the chipping and all those things. Third one, we face wear due to the mechanical fatigue, and also wear due to the chemical, which is normally we keep on getting the corrosion. So all these wears, we can able to have the problems like chipping during the usage of the tool, then the plastic deformation, breakages, means die or the tool breaks into two pieces, we can't able to use further, and due to the chemical the wear, we normally face the sticking or the soldering problem, which again leads to a lot of other activities needs to do on the tool to get it again in the usable condition. So all these adverse conditions we are keep on facing that one. So one thing is we keep on saying that how to tackle all those things. So to get these things, I will just yeah. So basically, these are different coatings we can able to use depending on the what kind of the wear pattern we are facing, and to overcome that one. So the protection coatings can help to protect against various forms of wear. Is the most common application of the thin film. and optimum protection against the wear requires a careful selection of the coatings. So we will see that what are the different coatings and how those can be able to use to overcome these kind of the wears, like adhesive wear, abrasive wear, which is a large in quantity, then the fatigue wear and tribological wear. For these different kind of the wear, we need the different properties of the coating, like a low coefficient of friction, low surface roughness, then high hardness, high compressive stress, so and so forth. So we need to tailor make the different kind of the different coatings for that particular application. So to improve the performance of the toolings, we have to basically concentrate on three things. One is a base material and its heat treatment. As we are using the different kind of the materials, right from high speed steel to D2, that is SKD11, then hot die steel, stainless steel, so and so forth. So we need to see that what is the right material for right application and its heat treatment, because the core properties are very much vital to run that tool on that application. So the heat treatment is more important. Once we have the proper material and the proper heat treatment, then we can look for the superficial thermochemical treatment, which gives the improved properties on the surface level. That is up to the say 100 micron, 200 micron, 300 microns. We will have the better surface properties than the core. So those properties can be achieved through say nitriding process or boriding process and other treatments. So the basic material, then the superficial thermochemical treatment, and then finally it comes to the coatings, that is the surface coatings. Because we will not have the smart materials like these nitrides or the oxides through the standard processes. So we have to have these unique materials through coatings. And with these three steps, we can able to have the appropriate tool to perform better, which will give the consistent quality of the end product as well as to save the cost of the tooling. So in our periodic table, I have marked with the areas with the red. These are the very vital elements through which we can able to have the variety of the coatings, which are the either nitrides or the borides or the carbides, or some. These are the ceramic based structures which gives the better surface properties. For example, if we see over here, titanium, if we react with the nitrogen, we can have the titanium nitride. Then zirconium, again with the nitrogen, which gives the zirconium nitride coating. Then titanium, aluminium nitride coating. Titanium, silicon nitride coating. So all these combinations and the nitrides or the oxides, we can able to form between these two blocks, and we have the various smart materials which we can able to use on our shop floor to improve the tool life, to improve the die life, or to improve the component life. So if we see what are the different coatings from these elements as well as gases. So one segment is the oxides. So we know that L2O3 or ZrO2, these are the oxides coatings which are available. Particularly L2O3 coating is being formed through CVD process and used for the cutting inserts. Another segment is the nitride or the carbide coatings. So titanium nitride, which is a basic coating, when this thin film technology starts way back in the 1960s, the base coating is a titanium nitride. So it starts with that one, then the new coatings started coming up: titanium carbide, titanium carbonitride, chromium nitride, titanium aluminum nitride, and nowadays still advanced coatings are there like titanium silicon nitride or titanium aluminum chromium nitride. So various nitride based coatings and the carbide based coatings are now available to enhance the tool life and get the better performance. Another segment where we see the problem with respect to the surface friction, then we should have to have the low coefficient of friction coatings. Then the diamond-like coatings falls under that category. So we get a very low coefficient of friction, less than 0.1, with amorphous carbon, with hydrogen and tungsten, or amorphous carbon with hydrogen and silicon, or with hydrogen, without hydrogen, amorphous carbon coatings. So all these different kind of the variants of the diamond-like coatings are being used to reduce the surface friction. So normally, if we see the diesel in diesel engines, a lot of components are being used, and to go from the Euro 4 to Euro 6, where the emission norms are very stringent, then these diamond-like coatings are very much useful and are continuously now used in the industry. And finally, in the DL diamond category, we can able to have the CVD diamond, which is the pure diamond coating in the thin film form, because we know that diamond we are getting it only from the nature in the crystalline form. But then we have the PCD, but it is very difficult to control the cost. In 1990 and onwards, the CVD diamond technology has emerged greatly, and it is giving the very good technology to have the non-ferrous cutting application. Then the another segment where we have the sulfides like molybdenum sulfide, tungsten disulfide, so on and so forth. And lastly, the borides. Titanium boron nitride, or the cubic boron nitride, titanium diborate, and all those things. Those also can be synthesized through CVD or PVD. Then all these coatings are in the form of thin film. So the coating thickness in the range of right from 1 micron or the several nanometers to 10-12 microns in case of the PVD. And with the CVD, we can able to go with the slightly higher one up to the 20-25 microns. So here you can see that we have the single layer coating or multi-layer coating or nano layer coating. The basic advantage why we have the these kind of the structures, because when we use these tools during the usage, definitely due to these wear and those one, crack propagation is there. So if we see, if we have a single layer which is a thick one, then the crack propagation is big, and then it goes directly touches to the base substrate or the base material, giving whatever the coating is there, that just gets popped off, goes off from the surface, and then we don't have the wear resistance on the surface. So sometimes single layer is not advisable. Then over a period with the research, people have started using the multi-layer coating. Means within a 3 micron or within a 5 micron, we have a 30 layers or the 50 layers. So that when any crack propagation is there, it doesn't go directly to the substrate immediately, but it finds the obstacle in between, and then the tool started lasting longer. Similarly, nowadays with the nano-based technological development, we have several nano layers. That is what I have mentioned, tens of nano layers in a total of 5 micron. So you can see that how the strength of that coating gets enhanced, and ultimately we have a better productivity. Again, ultimately it leads to the savings in the cost, and mainly having the consistency in the quality of the end product, because that is the more important: quality, quality, and quality. So now we'll see that how these coatings are being formed with a different kind of the methods, namely CVD and PVD. Before going to that, just general the idea, what are the hardness levels we get with these nitride or the ceramic based coatings. We know that with the up to the carbide, tool steels and carbide, we are having hardness, core hardness is in the range of around 600 to 800 HV. That is what we get the hardness in the base material. But since as we start getting the nitride coatings, then the coating thickness increases by 2 times or the 3 times. So here you can see that if we see the say basic chromium nitride or the titanium nitride coating, these are the basic coatings in the industry. There the hardness level is in the range of around 2000 to 2200 HV. And as we start getting the higher and high-end coatings, then it start increasing. For example, aluminum titanium nitride, which is in the range of around 3200 HV. We have some of the other coatings like concept coating. There we can have almost 3800 to 4000 HV hardness of the coating. And with the diamond, we can go up to the natural diamond hardness of 1000 HV. So as we progress having the smart coatings, we can able to have the different hardnesses with the different coefficient of friction, and all these can be tailor-made as per the application, whether it is a cutting tool or in the forming molding. Different segments are there, like hot forging, then pressure die casting, rolling, plastic molding. So all these different applications requires the different coatings with the different surface properties, which are very much tailor-made as per the requirement. So now I will just start with the CVD. CVD, the name itself suggests that it is a chemical vapor deposition. So this process is based on the chemical as a raw material to form the or to synthesize the coating. So the basic process is gaseous source plus we need to give the heat as activation for the gaseous source, which gives the solid film and the gaseous byproducts. So the thin film formation in this route is gaseous to solid. That is the transformation to have the thin film. Basically the reactive gases like say hydrogen, nitrogen. There is some. This is not completely coming up. Just a second. Okay. With this route, as I mentioned earlier, also titanium carbide, titanium carbonitride, then TiN, L2O3. These are the coatings can be formed through this process. But here the limitation is that this process is carried out at a very high temperature of 1050 degrees centigrade. So due to the such a high temperature, a lot of limitations with respect to the base material. So we can able to use this process only for the material which can withstand up to the this temperature, or there is an alternate way. We can process at this temperature and then do the heat treatment after coating, which again leads to the different kind of the problems. So if we see, this is the way the tools are being loaded in the CVD furnace. Here you can able to see the carbide inserts, then some of the toolings which are used in the press industries, then wire drawing dies, some of the punches. So all these different kinds of the tools are being loaded inside the retort, where the temperature is in the range of 1050 degrees centigrade. Normally in the industry, means in the process, this is called as a tree. This tree is being placed inside the retort. Then the gas distribution. For example, now if we want to do the titanium nitride coating, then for the titanium tetrachloride, TiCl4 is being used as a chemical source for the titanium, and with the help of hydrogen and nitrogen, it is being carried out inside the retort. And at the high temperature, those gases gets cracked, and they form the titanium nitride coating on the substrates. Now here, all these tools are being loaded or placed on the plates which are made up of the graphite, because we know that graphite only can withstand up to the this high temperature, maintaining its stiffness. So normally all the fixturing which is used for the holding of the tools in the CVD process is graphite. Since a gas goes anywhere uniformly, so even idea of the any component or the any die block, we can able to have the very uniform coating inside of the that surface. So here the masking is very difficult, and lastly, this process is a bit explosive process, because here a lot of hydrogen is being used. Then the byproduct of this process is hydrogen HCl. Due to this corrosive nature of the byproduct, we have to use the neutralization and then dispose it off. So overall process with the high temperature and the gaseous hazardous process, there are the certain limitations. So this is being used for the limited activity, and particularly nowadays this is being used for the captive purpose. In India, say Sandvik, Drilgo Seco, nowadays it is a Seco, then a Tegutech, a Kenametal, all those who are manufacturing the inserts, they are using the CVD process for coating on the carbide inserts only. For the steel substrates, it is a very less use due to the temperature limitation. So this is the coating machine and the development into the technology. You can see that on the left side, this is the CVD coating furnace. This has been developed way back in 1965 or 1970s. So you can see how the structure was there. Here the control panel, then the gas distribution. This is the retort where inside all the tools are loaded with a high temperature of 1050 degrees centigrade. And this is the chemical process the unit to neutralize the byproduct of this process. So this is a very old setup, and over a period now around 2010 and those one, after that then the very sophisticated machines has been started manufacturing and started using into the all in the industry. I would like to mention this thing. This is not the product say what I can say advertisement, but Iron Bond is one of the leading CVD machine manufacturer, and all these proudly say that in India, all these CVD insert manufacturers, what I have mentioned right now, all are they are using the Iron Bond CVD machines for the captive purpose. So this technology very well established, and on day-to-day basis they are using it for their captive purpose. Now further there is another development is there. Instead of 1050 degrees centigrade, now with the development, this temperature now has reduced, and now we have started doing the CVD coatings at the relatively less temperature of around 550 to 650 degrees centigrade. So it is near coming to the PVD process temperatures, which are having the additional advantages and started now using into the market. So this is related to the CVD part, how the process is there, and how there is a revolution from old technology to the new technology in CVD. Now I will just go to the PVD part, that is a physical vapor deposition. We know that everybody in the industry knows the different kind of the coatings, and these are getting synthesized through PVD process, that is a physical vapor deposition. Basically, under the PVD, there are the two categories through which these thin film coatings are being carried out. One is the sputtering technology. There and again there are the sub technologies are there, and another one is evaporation. With these two different sub processes are there. With the sputtering, one of the famous technology is a magnetron sputtering, which are having the certain advantages, but at the same time certain disadvantages. And with the evaporation process, we have the arc technology and the e-beam technology. E-beam technology means in the PVD route, the basic technology development is through the e-beam, electron beam evaporation. Through that, the thin film technology started. After that, then the arc technology comes in. So now we'll see what are the differences between these three technologies and which is the best suitable to from the commercial point of view as well as from the coating quality point of view. So this is the comparison between the electron beam, sputtering and cathodic arc. The type of the source means the coating material which is being used to do the PVD coating is in electron beam. It is a metal, so it is a pure metal like alone titanium or alone vanadium or alone aluminium. So there is a pure element is being used for in the e-beam, whereas in the sputtering or the cathodic arc we can able to use the metals as well as the alloys. That is a very important, because some of the advanced coatings like titanium silicon, with the proper concentration of the titanium and the silicon, such kind of the alloys we can't able to get it through the e-beam. But with the cathodic or the sputtering arc, very well those can be used and have a better properties of the those coatings. What is the state of the source? In the e-beam, electron beam, what are the metals we are using? Those are in the liquid form. Whereas in the sputtering of the cathodic arc, it is in the solid form. So in general, for the PVD, it is a solid to solid thin film transformation. Whereas in the CVD, it is a gaseous to solid. This is the difference between these two technologies. Now here you can see that the temperature used to deposit all these coatings through the PVD process is 400 to 450 degrees centigrade in electron beam, whereas sputtering or the cathodic arc we can go down to the 200 to 550 degrees centigrade. So by and large, PVD coating is carried out well below the tempering temperature of the tool steel. So there is no change into the core properties which are being generated during the heat treatment. That's why after the coating, no need to do any post-processing. Directly one can able to use that tool or that component on the shop floor or in the engine. Then the heating, here it is, heating is carried out with the help of argon ions. In the sputtering also it is argon ions, but in the cathodic arc process, argon or as well as metal ions. That gives the better impact on the tool surface, which gives the better adhesion, as we can able to see down the level. Then uniformity of the coating in the e-beam we get very good, or the rather uniformity is relatively good in all the three processes. But one of the major requirement is the adhesion of the coating to the substrate. The e-beam gives the relatively good adhesion, but the sputtering, where the energy level of the ions which are being produced with the help of a magnetron, those are on the lower energy ions are getting generated. So the adhesion is relatively less as compared to the e-beam, and as compared to the cathodic arc, it is very less. So in cathodic arc, since the bombardment is with the argon ions as well as the metal ions, of the say, titanium or the chromium, and due to the high temperature and the high energy of the ions, those gets embedded inside the material first initially, and then the coating will start on that one. So the adhesion levels are very good or the excellent in case of the cathodic arc technology. Coating thicknesses, which is the one of the requirement depending on the application. As you know that if we see the broaching application where the tolerances are very low in the range of say 2 micron, 3 micron. So there we need to have the titanium nitride coating of just 1 micron. If we give the 3 micron, 5 micron, 10 micron, then instead of cutting, we will observe the rubbing, and then there is no any component manufacturing over there. So whereas if we see the hot forging application where the impact load is very high, and there if we give the 1 micron coating, then the coating will not withstand with such a high load. So there we need to give 8 to 10 microns or the 12 microns. So depending on the application, we need to choose the appropriate coatings. And here you can see that with the electron beam, we can have maximum 2 to 4 micron coating thickness, whereas with the cathodic arc, we can go up to the 1 to 12 microns. So even near to the CVD process, we can able to have the coating thickness through the cathodic arc. So with the low processing temperature, then excellent adhesion and relatively high coating thickness. This combination allows to have this cathodic arc process commercially viable, as well as to have the better these smart coatings. So I will just discuss something related to the cathodic arc, because they in day-to-day applications, what you are using all these coatings, those are all getting produced through the cathodic arc process only. So I'm just going to concentrate more on the cathodic arc. This is the general setup of the PVD process. So here we have the vacuum chamber, then the tools which are loaded on the table, which is continuously rotating inside the chamber. We have vacuum pumps, then vacuum measurement units, heaters are there to heat the tools. Then this is the cathode, means this is a target of the, say, for example, titanium or chromium or aluminum titanium, of which we need to do the coating. Then the control panel, and then different kind of the power supplies are being used to synthesize and maintain the appropriate stoichiometry of the coating during the process. So this is a very important aspect of the using the different kind of the power supplies. Here the basic process, what happens initially after loading all the tools, a very high vacuum of 10 to the power -6 torr level vacuum is getting created, so that whatever the oxygen is there inside the material, that goes off, and we have the clean environment inside the chamber. Once we have the vacuum, then we start heating the tools. Get the temperature of the 200 or the 300 or the 450 degrees centigrade, depending on the metallurgy and depending on the coating. And once the temperature is achieved, then start the coating. How the coating starts? Now, on the left side, we see this is a long target. We call it as a cathode. So this is depending on the material of which we need to do the coating, that is the solid material of this cathode is there. So here we apply a very high current of around, say, 80 ampere, 100 ampere, 200 ampere, and due to that high current energy, on the surface the arc is getting generated. We see the arc in the sky. A similar kind of the arc is getting generated, and due to that arc temperature is in the range of 4,000 to 10,000 degrees centigrade. So at a high temperature, this titanium material or the chromium material start evaporating, and whatever the vapors are coming out, those are that material ions. So for example, titanium ion, which is having the positive potential. Now we are introducing the nitrogen gas as a reactive gas over there. So the nitrogen gas, which is in the N2 form, that also gets dissociated due to the plasma formation around the tools, and then it gets the nitrogen ions. So the titanium ion, nitrogen ion, they get recombined and reacted with each other. They form the titanium nitride. But now this titanium nitride is in the positive, which is having the positive potential. So what we are doing, we give the negative potential to the tools. So with this negative potential, these positive potential ions, they get attracted towards the negative potential surface, and they start bombarding at the initial stage. Once the bombardment is done, and with the appropriate adjustment of the different voltages, and then we start developing coating on the surface. And with this, we can able to do the coating of 1 micron to 12 micron, 15 micron, depending on that application requirement. Here, one thing is that this process is a line of sight process. Means what? Whatever the surface is seen by the cathode or by the plasma, that surface is only getting coated. Then the back surface is not getting coated due to as it is not seeing the cathode surface or the target surface. So we need to keep on rotating the tools during the process of say 2 hours, 3 hours, 4 hours, so that every tool gets rotated on its own axis and get the uniformly coated throughout the diameter as well as length of the tool. That one needs to keep in mind that this process is a line of sight process, not the gaseous process like the CVD, where the coating will be uniform even in the bore. So L/D ratio is a very important aspect when we consider what kind of the coating is done through the PVD process. So if we see the broad comparison between these two processes, both the processes are equally important to form the thin films. They have their own advantages vis-a-vis own disadvantages. So CVD, high temperature process, 1050 degrees centigrade, or nowadays 650 degrees centigrade, whereas PVD, low temperature of 200 to 400 degrees centigrade. Even nowadays, through the PVD, plastic is also getting coated. So the process temperature is still below the melting temperature of the plastic with the PVD. And then CVD is a gaseous, whereas the PVD is a line of sight process. CVD coating thicknesses are very high. So the open tolerance toolings like the inserts, roughing inserts are being coated with the CVD process. Whereas with the CVD close tolerances, where 1 or 2 micron precisionness is required, those are very well suited only through the PVD, not through the CVD. The different material restrictions are also there due to the temperatures, and then the heat treatment is required in the case of CVD, whereas no any treatment is required in case of the PVD. So nowadays PVD is being largely used for the all kind of the tool steel tools as well as components which are used in the wear and tear applications. I hope that it is you are okay with that. So now I will come to the coating thickness. Means characterization of these thin film coatings. There are basically 3 characterizations are being carried out. One is a coating thickness, second one is adhesion, and third one is the hardness of the coating. All these measurements are the destructive test. So sometimes it is very difficult to do the characterization on the tool itself. So we need to have the test coupon along with that coating batch and do the coating, do the characterization on that test coupon to correlate what we are having on the tool. So the calo test, which is being used for the thickness measurement, where physically the coating is being removed from the surface, and we can able to see these kind of the rings, where at the center portion with the no coating, and then it starts a first layer, second layer, third layer, fourth layer, or in the other case it is a bilayer coating, first layer and second layer. So all those the different layers we can able to see, as well as with a high resolution microscope we can able to measure what is the thickness of these coatings. So this is a calo test which is normally being used to measure the thickness of the coating. Then adhesion. Adhesion is being measured on the level of 6 levels, HF1 to HF6. And here what I have shown is that HF1, HF2 and HF3, up to these one, the adhesion levels are acceptable, and if it falls under the category of the HF4, 5 or 6, then you can able to see that the coating is getting peel off from the indentation. Then we can able to see that the coating adhesion is not good, and then that tool is not good to use on the machine or on the wherever it is required. So in this test, what we are doing it. Basically, this test is also called as a Mercedes test. We are taking the indent of load of 150 kilo with that indentation. Then we need to see under the microscope if any spalling is there or any cracking is there, like this one. Then we need to categorize that, and accordingly we can able to see that whether the coating is adhesive or not. This is the adhesion test. And third one is the coating hardness measurement. Now here we know that all these thin film coatings are in the range of 1 to 10 micron. So if we use the micro hardness tester, where the load is 200 grams or the 500 grams, then we will not able to get the true coating hardness. Rather, we will get the compound hardness of a coating layer as well as a core. So we need to have the nano indentation hardness, where we can able to apply load of just 1 gram or the 2 gram. So the indentation will be only in the coating of 5 microns or the 10 microns, and we can able to have the true coating hardness. So this is a way we have to have the nano indentation hardness tester, where through which we can able to measure the coating hardness. Now I will move to the applications of these coatings. Basically, as I mentioned, coatings are nowadays integral part of our life. Whether it is industry, whether it is household equipments like say bathroom fittings or any other decorative items, and all the industrial segments. So you can able to see that in the forming and molding, we can have the coatings. Then decorative or the luxury items, we can have the coatings. Cutting tools, then component or the aerospace industry, automotive components, where mainly, as I mentioned earlier, DLC coating is much popular for the automotive components, and then the medical. Now I will just give the two examples of these coatings with respect to the these segments. application wise, now if we see the cutting tools, we have the different kind of the inserts, then carbide solid shank tools, and another segment is a gear cutting tool, which is a bigger industry. Maybe in future with the e-vehicles, this segment may come down, but as on date, still there is a big potential and the big field is available. Here what we are looking for: high speed, high field machining, which during the milling as well as hobbing. Then we need the tough and abrasive workpiece material, that is the best material. Then the high thermal and mechanical loads, and the machining should be with lubricant or without lubricant, because nowadays a lot of machining activities has started without lubrication, that is a dry machining. So here I will not go into the normal coatings of titanium nitride or the titanium carbonitride. I will just explain with these two coatings, which are the very advanced coatings. One is aluminum chromium nitride. Probably you know the Alcrona. Alcrona means aluminum and chromium. That's why it comes the Alcrona. And then iron bond trade name, we also do the ALC iron coating, which our trade means iron bond trade name is crosscut. Another coating is titanium silicon nitride, which is nothing but the hard cut. This is here you can see that this is the transmission electron microscope photograph of the titanium silicon nitride. So here you can able to see that just it is a crystalline structure is in the nanometers. So this coating is really formed at the nano size layer, and the nanocrystals are being formed during the formation of the titanium silicon nitride. So what are the advantages? Here you can see that if we do on the ball nose, then these are the different coatings. Just I have considered for the comparison. You can see the yellow, which is other coating is titanium nitride coating. Then maximizer means aluminum titanium nitride based coating, and hard cut means titanium silicon nitride based coating. So with high speed machining and the milling, we can see that coating erosion is hardly any. So if we see the hard cut is this one, it is just the 0.05 mm or the 0.07 or the 8 mm with a machining length of 6 meter length. And even if we go up to the say 18 meter length machining, then also the wear is 0.1. So with these coatings, we have hardly any wear, but the machining length is very high. So that is a basic advantage of these coatings during the cutting tool application. Now, how much time I have? Hello.
Yeah, please continue.
Yeah.
We are able to hear you. Please continue.
Yeah. Okay. Okay. Thank you. Another application is forming and molding. In forming and molding nowadays, with this shift of Euro 4 to Euro 6, that is Bharat 4 to Bharat 6, we have the advanced materials like high strength, low alloy, or advanced high strength alloys. So these where also these steels are forming steels are having the thickness of more than 2 mm, means 7 mm, 8 mm sheet thickness are also being used for the some of the components, as well as different forming and molding applications like cold forging, then piercing, extrusion, tight tolerance, high pressure applications, rolling, pressure die casting, hot forging, plastic molding. So a lot of molding applications and the forming applications are there, where different kind of the dies are being used, like blanking dies, tailor-made welded dies, hydroforming is there, stamping is there, rolling is there. So for all these different kind of the coatings are required. Just I will give 2 examples. This is one of the stamping die. This stamping die is used for the manufacturing of the car door. And here you can see that sheet thickness is 0.7 to 1 mm sheet thickness, and sheet material is galvanized SPC coated sheet. If we do the plasma nitriding and the chromium nitride coating, as I have mentioned, chromium nitride is a base coating where the coating hardness is in the range of 2000 to 2200 HV. With that, we can able to have the 82,000 K strokes, means 1 lakh strokes. But if we do the advanced coatings, like the concept coating, where coating hardness is in the range of 3800 HV with a very low coefficient of friction. See how the unique properties, high hardness and low coefficient of friction. So it is a high hardness 3800 HV, low coefficient of friction 0.15. Whereas when we have the metal to metal friction, it is 1. And as we start having the lubrication, then we start reducing the friction between these two. So with the concept coating, we have the friction is in the range of 0.15 or the 0.12. With that, the strokes or the components which we can able to generate is more than 1,25,000. So that way we can able to have the with the same coatings, with the same dies, we have the better productivity. So the downtime, machine downtime is very less. Cost effectiveness is there. Ultimately, we have, and here the advantage is that the first component and 1,25,000 component, the quality is same. So the what I mentioned earlier, the scrap is very less. That is a basic advantage of all these PVD coatings. Another example, I will just put it. It is a draw die. This is a Fuso truck brake back plate. Is being formed through this die. The material is a D2, that is a SKD11 with vacuum heat treatment treated die. Now here you can see that a sheet metal is Fe418. So the strength of the material, tensile strength, is now increased. It is 410. And you see the coating thickness, it is a 6 mm thick. So it is a very thick, being a brake disc. And now if we see uncoated, we can able to hardly get the 30,000. But with the concept coating, we can able to cross 1 lakh component. There is no change in the dimensions of the die. There is no change in the dimensions of the component produced. There is no, and with such a high thickness and the high tensile strength, we can able to produce good quality up to the 1 lakh plus components without change in the quality. This is also another die, draw die, where the thickness is 3 to 5 micron with a material EDD12. This is a cover of the disc brake over there, and with the concept coating, you can able to see we have produced 2 lakhs component. So that much of the improvement is there. This is another example of the chassis. Whatever the four-wheeler car we are using it, down the level we have the chassis. This is a complete die block of the chassis, and these are the segmented dies. So here you can see the segments of this die block, where the material is SKD11 with a core hardness of 5860 HRC. Total die block weight is around 5 ton. This is the component being produced through this die. Here the sheet metal is E24 with a thickness of 2.8 mm thickness. So here already produced the 1,20,000 components, and still the die is running. These are the few applications with respect to the forming molding. Now I will go to the automotive components, because we know that this basically everybody is fighting towards how to reduce the pollution, and pollution is getting generated in the diesel engines, which are widely used in the commercial vehicles, where all the parts are getting rubbed, and due to that continuous emission is there. So to reduce this friction, we have to have the frictionless coating, but zero friction is not possible. So we have to have the minimum friction. Now minimum friction, we have seen just now in the concept coating, the coefficient of friction is 0.12. Still it is higher. If we go to the DLC coatings, that is amorphous diamond-like coating, then the friction is less than 0.1. And all these engine parts like camshaft, tappets, valves, piston rings, or the crankshaft, all these now started coating with the DLC based coatings to reduce here again reduce the emission, that is a CO2 emission from the engine, as well as increase the acceleration. So even if we increase the acceleration, there is very less friction, ultimately very less emission. So this is a long way, and all the OEMs like say Volkswagen or Skoda, then Hyundai, they have started using these coated components in the diesel engines. Now recently, the Indian brand like Mahindra and Mahindra or Tata Motors, they have also started looking into these advantage of these, and started having these coatings for their usage in their cars. Here one application, just this is not so much functional like the engine one, but here you can see that this is a hook which is being fitted on the near to the door to close the door and open that one. So we are opening the door so many times. So to reduce the wear as well as the noise when we are closing the door or the opening the door, the DLC coating is being done on that hook to protect the its wear and the noise level. This is one of the Volkswagen in the high-end model. All vehicles goes with this kind of the coated hook over there. Now just go to the another segment of medical. Since these coatings are corrosion resistance coatings, as well as the advantage is that these coatings are biocompatible. In the nature, we know that the blood is a highest corrosive media in the nature. So to fight that corrosion inside, and during the accidents or during the old age, we need to have the different kind of the implants which are need to be fitted inside the body. So to resist the corrosiveness of the blood, these coatings helps a lot. So in the body, if we see the heart implant or the hip instruments, hip implant, knee implant, ankle implant, so different kinds of implants what being fitted due to the various reasons. Those are all nowadays getting coated with say titanium nitride or aluminum titanium nitride coatings to have the better wear resistance as well as the corrosion resistance. This is that part goes inside the human body, but at the same time we are using lot of instruments during the operation. So here you can able to see some of the instruments I have shown over there. So these instruments are also during the operation gets in contact with the blood. So it needs to be the corrosion resistance. So these instruments are being coated with the different coatings. Another thing is the during the operation, very small time is there to complete that operation, and everything goes very fast and SOS basis. So it is better when the doctor is doing the operation, then he tells just give the yellow color tool, or just give the black tool, because there is very less time is there to complete that operation. So the color coding to have the effective on the these operational instrument is also done through these coatings. So this is another application of the coating during the operations and in the medical industry. Also, in the during operation, lot of light is being used, and due to that light, if we use the stainless steel these instruments, then the light glitters, and sometimes doctors or the nurses who are doing the operation, they find some difficulties. So to reduce the glareness of the surface of the these tools or the appliances, we do the different kinds of the coatings to reduce the glare. So these are the different applications are there in the medical industry. And now with the corona and all those things, everybody is started looking towards the antibacterial coating. So in the food industry, nowadays a new and the advanced coatings has come up, which has the antibacterial coating. So during the usage, if we have those coated one, we will not have the bacterial growth, because particularly say in our kitchen, we use the different kind of the mixers, or and the blades are there, and different instruments we are using it. If we keep it and keep it aside for the longer time during the usage, also some fungal growth is there. So to have the antifungal growth property over there, these some kind of the PVD coatings are developed, like titanium oxynitride, or some of these DLC diamond-like coatings are also useful to have the antibacterial coatings on those kind of the tools. So that is the recent development, and due to this pandemic and all these situation, this antibacterial coating is widely started using in the Europe and the US, and now slowly it is started demanding in Indian market also. So that is also one of the major focus area nowadays with respect to the PVD coatings. So last, just as I have explained, these CVD, PVD coating, they have their own limitations, own advantages, and with the PVD coatings, we can able to have the miracles and have a very good quality as well as the cost efficiency. With that, we need to concentrate on the core properties through the, as I mentioned, choosing the appropriate steel and the heat treatment, followed by the surface treatment, and then have the coating, appropriate coating for that particular application. Then we will be through with respect to the what we are looking for with respect to quality or the cost or environmental safetiness. With this, I will just close my talk, and now we can able to just discuss on what are the things are there.
Thank you. Let me just bring Mr. Sandeep Regi up. Sandeep ji, unmute कीजिएगा please.
Yeah. Thank you very much, Dr. Vivek ji. And thank you very much, Dr. Atul ji, for your nice presentation. And you know, a lot of things have come up, and we have really known that we were only thinking that these coatings impact us in our industry, but today we came to know that they impact our whole life, the whole human life, from the industry, from automobile to medical science to even the household utensils. So nice, and thank you. A lot of things have come up, and there are few questions which are there. So let me take few of them here. Yeah. So first question is from Mr. Karthikeyan. Is there any coating for powder metallurgy parts? So can you? Yeah.
Powder metallurgical part. Yeah. No, powder metallurgy, it is sintered at the low temperature. So we can't able to use the CVD based coatings for the powder metallurgical substrate or the tools or the components. We can able to use these titanium nitride or the aluminum titanium nitride PVD coating for the powder metallurgical tools.
Yeah. So another question is how to measure hardness above 3000 HV, whether it is by micro hardness or how?
As I explained in one of my slides, I will just go over there. Just a second. As I explained, these coatings are very thin coatings. It is, I will say, 60 times less than the our thickness of the hair. So it is a very thin, 3-4 microns. So to measure the hardness within a 3 to 4 microns, we can't use the micro hardness, because in the micro hardness tester, the load applied is say 50 grams or 100 grams, 200 grams. So if we apply that much of the load, then the indentation penetrates through coating and it touches to the base substrate. So we get the compound hardness. So to have the hardness of the coating itself, we need to use the nano indentation where the load applied is just 1 or 2 grams. So that the indentation doesn't penetrate through the coating and it gives the only true hardness of the coating. So we have to use the nano indentation.
Thank you very much, sir. The another question, can moly coating be is possible with either PVD or CVD?
Yeah, absolutely. Particularly nowadays in the dye industry, particularly molybdenum disulfide and the other lubricative coatings are being used or carried out through spray. But with the PVD process and particularly sputtering process, molybdenum disulfide or the other lubricant coatings is possible through the PVD process.
Yeah. There's another question. What are the common coatings for your kitchen utensils? How safe are they for human? And if you can elaborate on calo test, which code is followed for THK addition hardness test? So there are 4 questions in one. Yeah.
Okay. So I will just go to the first kitchen appliances, where particularly titanium nitride, then chromium nitride, then DLC coating. All these coatings are biocompatible. So even if we use during the our regular usage in the kitchen utensils, there is absolutely no adverse effect on the body through which, if anything, goes inside our body. So all these PVD coatings can be used as a biocompatible on all utensils which are used in the kitchen.
Yeah. So if you can elaborate on calo test.
Yeah. Now I will just go to the calo test. As I explained earlier, calo test is a destructive test. And all these coatings are the very hard coating. So it's a very specific instrument is available in the market. which is called as a calo tester, where we need to physically remove the coatings from the surface. After removing the surface with the ball, we get the different kind of the circles. That is a wear. Due to that wear, removing the material, then we will have the two concentric circles. One inner circle with a no coating and outer circle with a coating. And then there is a specific instrument is there with the high magnification of say 50x or the 100x. We have to measure what is the thickness between these two circles, which gives the what is the coating thickness of that particular coating.
Okay, thank you very much, sir. Which code is followed for thickness, adhesion, hardness test?
Adhesion testing.
Yeah.
This is the process is being carried out. Anybody can carry out this process on their shop floor. See, on the shop floor, we are having Rockwell C hardness tester. On that hardness tester, whatever load we apply on the indenter is 150 kilo. So wherever the coating is there, that part you just have the indentation on that, and that indentation you see under the high magnification of say 100x. There you will see these kind of the picture. If there is any cracks are there along that indentation, then depending on the intensity of the crack, we can able to say that whether that coating is adhesion is good or not, or the acceptable or not acceptable. So in the scientific language, there are the 6 figures are there. So out of these 6 figures, it is called as a HF 1, 2, 3. Up to these 3 levels, we can able to say that the adhesion is good. And if we see the more peeling off around the indentation, then the adhesion is not good with respect to the that coating on substrate. So this is the test one can use.
What is the code you follow?
What is?
What is specification you are following? Specification, testing specification.
Testing specification. Yeah, it is there. I will let you know. Right now, that number is there, specific number for this hardness tester as well as adhesion testing.
Okay.
Okay. Yeah. So the other question, which is, what is the time required for 12 microns in cathode arc PVD process?
Basically, there are the 2 types of the time we need to consider. One is a coating time, that is door close to door open, and another time is pre-preparation and the post-preparation with respect to the tool again go back to the customer end. With respect to the coating time, means a door close to door open, it will be in the range of 10 to 12 hours.
Yeah, thank you very much. So in hot forgings, are PVD coatings used for press forging dies or for extrusion punches tools only?
These PVD coatings regularly one can use into the hot forging. Right now, the big hot forgers in India, we are having like Bharat Forge or the MM Forge and those one. Regularly, we do these PVD coatings for them. So the PVD coatings are very well possible on the forging dies, and those giving the good advantage with respect to the increase in the productivity.
Yeah. Sir, can you share some case studies for increasing the die life?
Okay.
One or two in
I have already explained 1 or 2 during
this
one.
I think you were there. Those were there, right?
Yeah.
So yeah, can we do CVD PVD coatings on aluminum casting dies or pattern to enhance the life?
Means
He's asking for, I think, yeah, casting dies. Yeah.
See, basically, these coatings are done in high vacuum. So casting is having the high porosity. So there is one or two additional processes we need to carry out to overcome the degassing from those porosity of the casting. But certain coatings are possible on the casting.
So are you referring to vacuum impregnation?
No.
Coating?
Some kind of the degassing, some kind of the we carry out one or two processes so that the whatever the debris or the foreign particles are there in the porosity, we take out first that one and then carry out the coating on that.
Okay, but it's possible, like getting pattern and aluminum casting dies to enhance the life, right?
Yeah.
So what's the time taken in these coatings in general, and how much is the cost per square inch? Is there any source doing these coatings in north region? So Mr. Mandral from north of India, so he's asking this question.
Presently, for the north, we are servicing from the Pune only. So what we are doing it, we are getting the dyes or the tools from the north, Delhi, Gurgaon, Manesar, Chandigarh to Pune, processes and give it back to them. Right now, we don't have the coating plant in Delhi. We have the plants, but not immediate.
So what is the temperature at which PVD is done? And is there any adverse impact on core properties of parts like hardness drop, structure change, etc.?
As I have explained, the PVD temperature is from 200 centigrade to 450 degrees centigrade.
Voice is not clear.
Sir, your voice is cracking.
Or HSS is.
So your voice is cracking. If you could, yeah.
You can repeat, sir.
Please repeat, sir.
Yeah. Now it is okay.
Yes.
Yes.
It's okay.
Now PVD coating temperature, as I explained earlier, it is 200 degrees centigrade to 450 degrees centigrade. Now we know that tempering temperature of the say D2 material or HSS material, it is 530 to 550 degrees centigrade. So the PVD coating is carried out well below the tempering temperature of the tool steels. So there is no impact on core properties of the these tool steels, as we are not touching to the tempering temperature of the material. So absolutely no change in the core properties. We can have very well coating on the surface.
Yeah. So if all the questions are over, I think. Yeah. So I think thank you very much.
Small question, small query.
Yes,
normally in kitchen they use the Teflon coating on the tawas and all this thing. So
right,
how it is done and how safe that Teflon coating is there? Because this is the question asked to me from my wife. So I don't have the answer.
Basically, sir, Teflon coating is done in not in the vacuum, so it is atmospheric pressure. That is the first, and it is just acts as a non-sticking one. So it doesn't have the hardness. So the wear properties point of view, it doesn't work.
It wears so fast.
Yeah, correct.
But is it dangerous for the human consumption? Because it will go in the food also.
Yeah, sometimes it goes in the food also. It is a bit dangerous because it is a Teflon, so it is a plastic base. So we need to definitely take care of that kind of the things.
Thank you.
Yeah, there is one last question. What will be the difference in life of forging die with HT plus PIL? And HT plus PI pin plus
Plasma
PVD.
hydriding plus PVD.
Yeah, it is a good question, and directly related to the quality as well as the cost. Now, basically, with the coatings, by and large, the life improvement in the forging industry is from 50% to 200%. Because for the some of the applications where the forge component is smaller one, where the impact is less, then we can able to go to the even 200% life improvement. And where the big congruent type big components are there, then it may be in the range of 80 to 100%.
So yes, thank you very much, sir. All the questions are now over, and now it's already 9 o'clock. So it was very nice, heartening to listen to all the PVD and CVD coatings, and understanding the difference between them and understanding the nitty-gritties of it and how it impacts the human life. That was more very nice information. And thank you very much, sir. Thank you very much for taking your time, and thank you very much all the participants for taking your time out. And
Okay, thanks a lot for
thanks
hearing.
a lot. And and good night, and nice weekend to all of you. So signing off from Mumbai. Thank you.
Thank you. Thanks a lot.
Thank you so much. Thank you all for attending. Thank you.
Thank you.
Thank you all.